All right, so one important property of a vector space is its dimension. In the Rn's, the dimension is always just the n, right? Like R3 is 3-dimensional space. R2 is 2-dimensional space. So the definition of dimension is the number of vectors in a basis for the space. So for R2, for example, the standard basis is 1, 0, and 0, 1. 2 vectors in that basis, the dimension is 2. Okay. So for each of these vector spaces that I've created here, we're going to find a basis, which means a linearly independent set that spans the whole space. And then the number of vectors in that basis defines the dimension. So we're going to state the dimension. All right, so I have a vector space V defined as all the vectors that look like 2a plus c, b plus d, a minus c, and b plus 3c, where a, b, c, and d are any random numbers in the real number system. All right, so a basis, I need first let's think about a spanning set, right? So I'm going to try to pull this apart like in parametric vector form. So all my vectors look like something times a plus something times b. All right, so my first entry is going to be 2a plus c, so I need a 2 for a and a 1 for c, and the other 2 get zeros. Second entry is b plus d, so I need 1 for b, 1 for d, the other 2 get zeros. A minus c, so I need a 1 in a, a -1 in c, the other 2 get zeros. And b plus 3c, so a 1 in my b vector, a 3 in my c vector, the other 2 get zeros. All right, so the vectors I've written down here, 2, 0, 1, 0, 0, 1, 0, 1, 1, 0, -1, 3, 0, 1, 0, 0. They form a spanning set, right? Because that means that if you take a linear combination of them, you can create any vector in the set. So I've basically written this as, this is my set V. I just expanded it into parametric vector form. So V is the span of those 4 vectors. Are those 4 vectors linearly independent? They are, yeah. And if you weren't sure, how could you verify? Yeah, I could put it in a matrix, RREF, and what would I be looking for? Pivot in every column, yeah. So these are a spanning set, and they are linearly independent, and you could check by doing a row reduce, pivot in every column. So my basis is made up of those 4 vectors. Okay, so there's my basis. 4 vectors that span the whole space and are linearly independent. So what is the dimension of my vector space V? 4. It's 4 vectors in the basis, its dimension is 4. All right, here's another one. W is the set of all vectors A, B, C, D. So 4 entry vectors such that A plus B minus D equals 0. So this is basically a system of equations. It's one equation, but you've got 4 unknowns here. So if I were to translate this system into a matrix, an augmented matrix, it would look like 1, 1, 0, C's, -1, augmented with a 0. That's my whole matrix, because there's only one equation. So I don't even have to RREF, right? I can tell what variables are pivots and what variables are free, right? So A is my only pivot position, and then B and C and D are all free variables. So this says that if I was going to write this in terms of the free variables, I would say A is -B plus D. B, C, and D are free. So to put it in parametric vector form, I would have A, B, C, D equals and then I have to have a vector for each of the free variables. All right, A is negative B plus 1D, and then B, C, and D are all free. So for B, they get a 1, C and D get zeros, C is free, so in the C entry, C gets a 1, the other two get zeros, and then D gets a 1 in the D entry, the other two get zeros. So when you solve a system and put the solution in parametric vector form, those vectors from parametric vector form always form a basis of the set for the null space, right? When you're looking at the null space of a matrix, which is what we just found because it was equals 0. So those three vectors form a basis. So what is the dimension of this space? Dimension of W? 3. Because there are 3 vectors in the basis. All right, I've got a 4x4 matrix A here. I want to find a basis for the null space. So this is what we learned last class. So it was a good review. A basis for the null of A. So what was the definition of the null of A? Oh, the dimension of the null space is the number of free variables. That's from your reading. That's good. Yes. So it's the number of all vectors that I could multiply A by, the set of all vectors that I could put here and get the 0 vector as a result. So all possible things there. So these are x1, x2, x3, x4. I want to describe what those vectors look like that will give me 0. So you take A and you augment with 0 to solve this thing. I'm not going to copy this whole thing down. So you augment with 0 and you're going to end up with 1, 0, 0, 0, 4, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Augmented with your zeros. All right, so if I want to write the solutions here in parametric vector form, my pivots are x1, x2, and x1, x3, and x4. x2 is free. x2 is the only free variable. So if I'm going to write out my solutions, I have x1, x2, x3, x4. I want to write them in terms of my only free variable x2. So x1 is equal to negative 4x2. And x2, x3, and x4, what do those equal? Well, x2 is free, so I put a 1 there. What about x3 and x4? They're both 0, according to the matrix I wrote down. This says x3 equals 0, x4 equals 0. So this vector, negative 4, 1, 0, 0, is a basis for the null space of A. So my basis is that one vector. So any multiple of negative 4, 1, 0, 0 is in the null space. That's what it means to be a basis. The linear combinations of the vectors in the basis form the whole space. All right, what is the dimension of the null of A? 1, because there's one vector in the basis. Okay, so is there a shortcut for finding the dimension of the null space of a matrix? Yeah, the number of free variables. Because the number of free variables dictates how many vectors are going to be in parametric vector form, and that's also the number of vectors in your basis. So the dimension of null A equals the number of free variables in AX equals 0. All right, anybody remember how we find a basis for call A? You take the columns. Yes. Which ones do we keep specifically? The pivot columns. Yeah. So you have to take the pivot columns from the original matrix. So our pivots are column 1, column 3, and column 4. So I take 1, 3, and 4 from my original matrix A, and those form a basis for call A. So I get 0, 5, 1, 0, -2, 1, 0, 4, and -5, 14, 2, 10. So what's the dimension of the column space of A? 3. 3 vectors in the basis. So I was looking at when I row reduced, I found pivot, 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 column 1, column 3, column 4. So you take 1, 3, and 4 from the original. Is there a shortcut to finding the dimension of the column space? The number of non-free variables, which we call pivots. So the dimension of call A equals the number of pivot columns of A. Okay, I have some subspace of P2. That means that maybe not every element of P2 is in there, but all the elements are quadratic polynomials or lower. And they are spanned by these 4 polynomials, right? So you can build every element of H by taking a linear combination of these 4 polynomials. I didn't tell you that this is a basis, though. I just said this is a spanning set. So what's missing? If you have a spanning set, what's missing from the definition of basis? Linear independence, yeah. Are these 4, quote, vectors linearly independent? No, how do you know? Yeah, so 3t squared plus t and 6t squared plus 2t, the one's a multiple of the other, right? So any 2 that are multiples of each other, one of them is redundant. So I'm going to get rid of 6t squared plus 2t. 2t plus 1 and 10t plus 5, those are multiples of each other. If you take 2t plus 1 and multiply by 5, you get 10t plus 5. So I don't need the second guy. It's redundant. Now the 2 that remain, is one a multiple of the other? No. So now I have a linearly independent spanning set, making it a basis. So what's the dimension? Two. There are 2 vectors in the basis. All right, so that's the whole demo.